Hello, it's me, Alwyn. Today I'm going to talk about the recent LIGO result from October 16th, 2017. Well, that was when they released the news, but actually it happened August 17, 2017. Let's start by explaining what is a neutron star and why is it important to see two neutron stars crashing into each other. So if you have a really massive star, eventually what happens is that fusion of the inside cannot hold up the weight of the star. The weight of the star is huge, and in order to hold it up, you need to create a lot of energy in the center and have that energy flow out, and the pressure of that energy flowing outwards is what holds a star up. In order to produce that energy at the center, you need nuclear fusion. The problem is when a star fuses hydrogen into helium, helium into carbon and oxygen, all the way up to iron. After you reach iron, you don't get energy anymore. You lose energy. Iron is poison for a star. It eats the energy. The reason is this. An iron atom has a large number of protons. I believe it's 26. When you have 26 protons and you have 26 protons on the other side, you have to convince them to come together somehow. And positive charges repel. And this takes a large amount of energy. At the point of iron, there are so many protons on both sides of the atoms that it takes more energy to bring them together than the energy you get out. And so iron is poison. So when you lose this thermal support, we call it thermal because it's heat energy. When you lose thermal support, you need to have another version of pressure in order to support your star. The next option available to us is electron degeneracy pressure. It's a quantum mechanical effect. If you have one electron and another electron, usually they cannot share the same space. However, in quantum mechanics, the laws are that they can share the same space as long as they have different momenta. When you have a very compact core of a star, you have a large number of electrons all trying to share the same space. So what happens is that they have to have different momenta. And in quantum mechanics, things are discrete, which means that the momenta levels that they occupy are discrete. This means that every additional electron has to have a finite multiple of the momentum, more than the previous electron. And what this ends up making is a large mass of electrons with a large amount of momentum. And momentum is basically pressure. These electrons, you can think of them as bouncing around very quickly. And that bouncing around very quickly, because of their high momentum, is what produces electron degeneracy pressure. And this is what holds up a star if it cannot support itself thermally. The problem is that a star might be so heavy that even electron degeneracy pressure cannot hold it up. So then what do? Well, now we've got this iron core of a very heavy star. There's still elements outside other than iron. For example, there's carbon and oxygen, helium, hydrogen. All this stuff is pressing on the center of the star, and the center of the star made of iron cannot hold itself up. What happens is that the pressures become so high, electrons are forced into protons. And they're forced to combine. Electrons are negatively charged protons are positively charged. Combining the two creates a neutron and a neutrino. In this process, we turn our gas of protons and electrons, mostly, hydrogen. There's also protons and electrons in iron, of course. We turn this proton and electron mixture into something that's mainly neutrons. And the great thing about neutrons is that they can provide the pressure we need. Neutrons are 2,000 times heavier than electrons. And what this means is you can pack them into a smaller space. Their de Broglie wavelengths are smaller. An intuitive way to think of this is that if you have an electron, it's so light that it's really easy to make the electron whiz around and take up a lot of space. But if you have a neutron, it's heavy, so it prefers to sit and not take up a lot of space. These neutrons that now comprise this neutron star hold themselves up through neutron degeneracy pressure, which is much stronger. Now again, since neutrons are 2,000 times heavier, they're going to take up 2,000 times less space. So let's talk about that for a second. If you have a star like the Sun, it's not going to become a neutron star, but let's just talk about it as an example. The Sun is 100 times larger than the Earth. You can fit 100 Earths in the Sun. If something like the Sun collapsed into a white dwarf of the same mass of the Sun would take up as much space as the Earth. So imagine compressing the Sun by 100 times and you get something like the Earth. And that compression is what you need for electron degeneracy pressure. Now you need 2,000 times more compression for neutrons. So neutron stars are the same size as the Earth except divided by 2,000. The radius of the Earth is roughly 6,000 kilometers. Let's divide by 2,000. That's 3 kilometers. So a neutron star fits the entire mass of the Sun in the size of a single city. In the process of compressing this enormous star with its magnetic field into a smaller space, you take all of this magnetic field along for the ride, and you compress that as well into a tiny, tiny space. And so what happens is you get these fields that are 10 to the 12 times as strong as Earth's magnetic field. And that is amazing. That is 1 with 12 zeros. Let's see. 10 to the 6 is a million. 10 to the 9 is a billion. 10 to the 12, I believe, is a trillion. It's quite a large number. The other effect that you get is that angular momentum must be conserved. Angular momentum is an object's distance from the center times its velocity tangential to that distance vector. When you decrease the radius, that means everything has to be moving a lot faster. The conservation of angular momentum means that the neutron star you get is going to be spinning very, very quickly. What we see in nature are what's called millisecond pulsars, neutron stars that are spinning 1,000 times a second. If you have a 3-kilometer radius object spinning at 1,000 times a second, roughly speaking, the surface is moving at 3 kilometers a second times 1,000 hertz, or 3,000 kilometers a second. You can put some factors of 2 pi in there and get 18,000 kilometers a second. That's fine. The speed of light is 300,000 kilometers a second, and so you get this object whose surface is spinning at 1/100th the speed of light. And that is getting really close up there. So you have this neutron star, this extreme object composed mostly of neutrons, and who knows what else in the core at those high pressures, spinning extremely quickly. It's the mass of the Sun, it fits in a city, it has these enormous magnetic fields strong enough to rip virtual particles into existence. It literally rips the vacuum foam and turns it into particle-antiparticle pairs. It is so strong it disturbs vacuum space itself. This extreme object, bending space-time at nearly the same amount as a black hole, it's not there yet, but it's close. This object is a neutron star, and it's really great. Now let's have two. If we have two neutron stars spinning around one another, orbiting each other, their distortions on space-time are time-dependent. They fluctuate. If you put your finger into a pond and move the finger around, you are going to get ripples in the pond. For the same reason, neutron stars are going to ripple space-time. You need two of them because they have to be orbiting around each other and accelerating each other. These two neutron stars orbiting each other emit what's called gravitational waves, the analog of our ripples on the pond. Those gravitational waves are distortions in space-time. What is a distortion in space-time? What is space? What is time? Space is what separates two objects from one another. Time is what separates two events from happening at the same time. Space is ultimately measurement. Time is ultimately measurement. Space you can think of the distortion of space as taking something that you think to be a meter, and if you distort it, then suddenly the meter is maybe a little more than a meter or a little less than a meter. Similarly for time, you may have heard of time dilation around black holes, something that you think is taking a second. For example, a watch ticking every second around a black hole. Since the space-time is distorted, that measurement of time is different. So this gravitational wave changes the measurements of space-time as it passes through you. As it passes through the Earth, it changes the size of the Earth just by a little bit. So imagine the Earth is this, it's not exactly round, it's my hands, but imagine this is a circle. As a gravitational wave travels through the Earth, part of the Earth gets shorter and part of the Earth gets longer. And then in the next cycle, the short part becomes long, the long part becomes short. This is a gravitational wave, and this is what LIGO and gravitational wave interferometers try to measure, these tiny changes in length. These changes are so small that the surface of the Earth, well, suppose we have a wave whose amplitude is 10 to the minus 15, and this is, I think, fairly typical. The radius of the Earth is 6,000 kilometers. This is 6 times 10 to the 9 meters. 6 times 10 to the 9 times 10 to the minus 15 is 6 times 10 to the minus 6. This is millionths of a meter, and that's the change on the entire Earth. LIGO is something that's kilometers wide, and so what they are measuring is something on the scale of the fraction of an atomic nucleus. It's quite amazing, but they measured this. As two neutron stars distorted the space-time around them and sent ripples across the cosmos, they reached us here on Earth, and we detected it using these gravitational waves. We detected these small changes in the distances between 2 points. We did it for 2 different arms, so here's a set of 2 points and here's a set of 2 points. That's one observatory, and then we had a couple of these. We have 2 of these in the US and Virgo as well. So in total there are 6 arms, and they are all being compared to each other. That is how we measured gravitational waves. Why is this important? Well, as soon as we measured the gravitational waves, we had lots of telescopes point to where it came from. And they saw electromagnetic waves. So we used light and gravity to observe the same event. Since we can see the same event through, multiple angles, so to speak, it lets us get a better sense of what's going on. And so we knew from these observations that 2 neutron stars had collided. In the process, they formed a large amount of gold and heavy elements that require a lot of neutrons to be produced. You may know intuitively, if you've ever taken chemistry, that the heavier an atom is, the more neutrons it has per proton. Atoms become more neutron-rich as they get heavier and heavier, and in order to make them, you need a source of neutrons. And we think neutron-star mergers, these collisions, form all of these neutron-rich elements. For example, gold. In this merger, we believe that roughly 100 times the mass of the Earth was produced in gold alone, and then a bunch of things were produced in other elements as well. That's a lot of gold. Suddenly, the scarcity of gold on Earth doesn't seem so scarce anymore, does it? 100 times the mass of the Earth was produced in gold alone from this event. That's one thing that's cool. The other things that are cool, we can compare these observations to our simulations of neutron-star mergers. We tried to detect neutrinos. No neutrinos were observed. We used this event to measure the expansion rate of the universe. We know what galaxy it's in, and we can use radial velocity, Doppler effect, redshift, blue shift kind of thing to measure the velocity of the galaxy. And the shape and power of the gravitational waves tells us the distance. And so we measured Hubble's constant, the expansion rate of the universe, using this gravitational wave. To summarize, I've explained how a neutron star is formed, why are they such extreme objects, how they produce gravitational waves, and I've summarized some of the observations. I hope this has been an educative and interesting experience for you. Thank you very much.